All right, let's get started. Are we doing all right? Okay. I have updated the scores on Blackboard, so if you had that one multiple choice question from the exam that we talked about that it didn't have 2 correct answers, but the wrong one was on the key, but I didn't change it if you picked the wrong one, but I gave you the points if you picked the right one. So if you picked D, then you should have gotten 2 more points. So you can check that, check your score, but I think we got it. If you think you missed it or something, let me know and we can look back at it and figure it out. All right, so today we're going to talk about solutions. We finished gases on Tuesday and did those demos and talked about those relationships. That is the rest of chapter 5. So now we're into chapter 6, talking about solutions. So what happens when you have something mixed with something else? All right, a solution is something that we've used a lot already, something that you probably know a little bit about just from the lab stuff that we've done. But we want to talk about a few specifics of how we identify solutions, some vocabulary that we're going to use, and some ways that we calculate the amount of actual stuff in our solutions. So first of all, a solution is just a homogeneous mixture, so something that's mixed very well so that you can't pick out the individual parts of it. It can still be separated by physical means. And any solution is going to have 2 parts. A solute and a solvent. You heard those words before? People? Maybe, maybe not? Yes? Okay. So what is the solute and what is the solvent? Anybody have a good working definition that you use of those? Like what? Yeah, it has to do with dissolving. So which one is dissolved in which? Yeah, solute is dissolved in the solvent. So really the only thing that's really identifying about these two is that there is less of the solute and more of the solvent. The reason we have to keep our definition so general is because even though when we think solution, we usually think a solid dissolved in a liquid, that's not always how it works. And you can actually have any state dissolved in, well, almost any state dissolved in another state to get a solution. So solutions can be solid, solute in liquid solvent. That's probably what we most think of when we think about a solution. But you can also have a gas solute in a liquid solvent. And you can also have a liquid solute in a liquid solvent. So some examples of that, a solid solute in a liquid solvent might be something like salt water, where the salt is dissolved in the water. So salt is the solid and water is the liquid. Gases can be dissolved in liquid also. So for instance, hydrochloric acid. Which we've used, is HCl, but the actual pure compound HCl is a gas. Hydrogen chloride is a gas. So the hydrochloric acid HCl that we use in lab is actually that gas dissolved in water. We can also talk about things like oxygen gets dissolved in water, which is how fish can survive because they can extract that oxygen out of the water, and so on. And then a liquid in a liquid, that's something we can do all the time too when we dilute some sort of pure liquid by mixing it in with another type of a solvent. So something like an ethanol water mixture. Ethanol and water are miscible, they can mix, and so you can dissolve some ethanol, which is a liquid, in some water, which is also a liquid. All right. You can also have solvents that are non-liquid. So you can have a gas solute in gas solvent like air. So air is really a solution because it's a homogeneous mixture of some different gases. What would be the solvent if we think of air as a solution? What would be the solvent? What would you call the solvent? Not oxygen, because oxygen isn't the major component of air. If our definitions are the solute are the things that have less and the solvent is the thing that has the most, what does air have the most of? You know? Not carbon dioxide either.
Hydrogen.
Nope, that would be really dangerous because hydrogen's flammable. It's nitrogen, yeah. Air is mostly nitrogen. Mostly nitrogen. So the solvent in air would be nitrogen, and the solutes would be all the other gases like oxygen, carbon dioxide, water, whatever else. And then you can actually also have a solid solute in a solid solvent. One example they give in the book is brass. Brass is an alloy, sometimes we talk about. It's a metal that has copper and I always forget this one. Nickel, is it? Zinc, copper and zinc. Brass is an alloy of copper and zinc, which makes it resistant to oxidation. You know how copper turns that green color, like if you have a copper statue and eventually it turns green because it oxidizes? Brass doesn't do that. So brass is like what they make metal instruments out of, like trumpets and saxophones, that kind of thing. And that's because when it is combined in a solution with zinc, that changes its properties, changes its hardness, changes its behavior a bit. But really, if you zoom in at the atomic level, what you see is mostly copper with zinc atoms mixed in there. So it's really a solution of a zinc solute in a copper solvent. Lots of different ways you can define a solution, but it's always a homogeneous mixture of some solute, small amount, and a solvent, large amount. All right. Sometimes, occasionally, we have a situation where these definitions don't hold. And the main example of that you'll see is water. Water is not totally always, but almost always solvent. I'm talking here specifically of liquid water. So you might find, like, if you need to make some extractions, or I think we're going to use it for an extraction later in the semester, you can buy 95% ethanol, which is 95% ethanol and 5% water. But it's listed as a 95% ethanol solution. That's kind of opposite, right? Because that means that there's way more ethanol than there is water. Or you can buy whiskey that is 55% alcohol. Well, if it's 55% alcohol, then it's really just everything else solution in the alcohol solvent. So because those are water solutions, they're often still named that way. They're often kind of given these really high concentrations because water is almost always the solvent. So if you're trying to identify a solute and a solvent, you're usually pretty safe with, if there's liquid water there, that the liquid water is going to be the solvent. And in most of the examples we do in this chapter, it's going to act as a solvent. All right, a couple more definitions about solutions, and then we'll get into some of these measurements. All right, let's talk about electrolytes. So last week, or maybe the week before, we talked about that when we were talking about intermolecular forces, we talked about things being dissolved in water means that the water molecules surround those individual particles, either ions or molecules. The water molecules are surrounding them because they have similar intermolecular forces to the water. So what are electrolytes? Has anybody heard that term before? It's in Gatorade. Everybody always says it's in Gatorade. Do you know what it is? Yeah, it's what? Yeah, so it's like salts, potassium, sodium, stuff like that. What do those things have in common? They don't actually give you energy. You need macronutrients for that.
Well,
That's water. Water stops you from being dehydrated. What? Yeah, actually throughout your whole body. So you don't just need water, you also need to be able to pass electric currents through your body. That's how your nerves work, that's how your muscles get triggered, all that kind of stuff. So electrolytes, the reason it's called electro is because it has something to do with passing electricity. What types of particles need to be dissolved in a solution in order for that solution to pass electric current? You know? What do you need to be able to pass electric current? I'll give you a hint. You can't pass electric current through pure water. Pure water does not conduct electricity. What does water need in it in order to conduct electricity? Yeah, it needs ions. It needs charged particles. So charged particles in solution can conduct electricity. And that's what electrolytes are. So electrolytes are the charged particles that allow electricity to be conducted. We can separate materials into three categories with respect to their electrolytic behavior. We can talk about strong electrolytes, weak electrolytes, and non-electrolytes. A strong electrolyte is any compound that completely dissociates into ions in solution. So dissociates means breaks apart. So an example of that is sodium chloride. If you take some solid sodium chloride and you put it in some water, not exactly a chemical reaction, we're just kind of describing a process here. You put it in water, you now have aqueous sodium chloride. That doesn't look like much of a change, but as we talked about last week, what that really means, or the week before, what that really means is that you have separate sodium ions that are surrounded by water that are dissolved, and you have chloride ions that are dissolved. So when we say aqueous sodium chloride, what we really mean is that the sodium and chloride ions have broken apart. They're individually surrounded by water molecules, and so there's now charged particles in that solution that can conduct electricity. And that's what makes it a strong electrolyte. So any ionic compound that is highly soluble in water, that dissolves in water, is a strong electrolyte. It will break apart, and they're all strong electrolytes. But they're not the only strong electrolytes. There's a category of molecules called acids that we'll get more into in the next chapter. And certain types of acids can also be electrolytes. So if we take some HCl, hydrogen chloride gas, which is just a covalent compound, H bonded to Cl, and we dissolve that in water, it actually does react with the water, and it makes this strange H3O plus ion called hydronium. And we'll get into this more in the next chapter, and chloride. Excuse me. Thanks. So these are now aqueous ions as well. So what you'll see is that if you take a solution of hydrochloric acid and you try to pass electricity through it, that electricity will actually pass through it. If you try to do that with a weaker acid like acetic acid vinegar, it doesn't work so well because that's a weak electrolyte. But strong electrolytes like ionic compounds and acids will completely break up into ions and therefore be able to pass electricity through them. All right, so that we can define our other categories from that one. So weak electrolytes are kind of like in between. These are compounds that partially dissociate in water or in solution. Right. So it only makes a few ions, not a whole lot. And the way we can express that is if we take one kind of classic example is vinegar or acetic acid. If we do that same kind of acid equation that we did above, this is acetic acid. A 5% solution of acetic acid in water is vinegar. So if we do that same thing, the way we can draw this is by actually giving two arrows. One going forward that's really small and one going backward that's really big. And this is telling us that is actually kind of staying on the left side of the equation. So only a little bit of products are forming. Mostly the stuff is staying put and not actually doing this. But the little bit that does produces those same hydronium ions and acetate ions. Whoops. C2H3O2 minus. So this can produce ions, but because of the way that it is structured and the way it reacts, it mostly doesn't. It mostly just stays neutral. And so that makes it a weak electrolyte. Only a little bit of ions get in solution, so it can only conduct electricity a little bit. And then the third category are the non-electrolytes. Which do not form ions in solution. So an example of that is like sugar. So sugar, sucrose is C12H23O12. Is that right? Hold on. Just look that up, make sure we got the right thing here. H22, sorry. Okay. So if you take solid sucrose, which is table sugar, you know, the regular white stuff, and you dissolve that in water, it does dissolve. I mean, you've seen sugar dissolve in water, right? Yeah, okay. So we do make an aqueous solution of sucrose, but we don't make any ions. Nothing breaks apart into charged particles there. You still have the entire sucrose molecule. It's now just surrounded by water. So it still goes into solution. It still dissolves, but it does not dissociate. It doesn't break apart when it dissolves. And that's sometimes a tricky thing to keep straight, because when you're watching it happen, you can see the little bits of sugar going away, and so it seems like it's going away. But it's at the molecular level, the molecules are actually staying together, and that's why it's a non-electrolyte. It's not breaking apart. It's not forming any ions in solution. Okay, so let's get back to Gatorade then. But why does Gatorade have electrolytes? They don't give you energy. What do you need them for? Well, we said what we need them for. Why would you need more of them by drinking Gatorade?
So when you're running,
Okay, but we already said that it doesn't contain energy. Energy is only contained in carbohydrates, proteins, and fats, not in ions. Yeah, when you sweat a lot, it's kind of salty. If you ever sweat and it like drips in your mouth or whatever, you lick someone who's sweating, I don't know. It's salty. What? It burns your eyes, yeah. And that's because those ions are coming out of your body when you sweat. So if you're sweating out all these ions and you're only replacing the water that you're losing, eventually you're not going to have enough ions in your body anymore. That's the problem. And it's particularly a problem with sodium. If you lose too much sodium, you can actually die from it. Now, this is only an issue mostly for people who are sweating a lot. So you're talking about like running a marathon or doing really extreme outdoor type work for a long time, which is why a lot of Gatorade is just marketing. Because if you're just running for half an hour, you don't need to replace your electrolytes. You probably still have plenty. But if you're really doing, you could probably just drink water. But if you're really losing a lot of those salts through your sweat, then you need to replenish them. You don't have to do it with Gatorade either. You can just eat some salt, or eat some like potato chips or whatever, and it's the same effect. Gatorade comes from, I think the story was they analyzed some football players' sweat at the University of Florida and decided that they should formulate a drink that had the exact same concentrations as what they were getting out of the people who were sweating.
So why when you're sick or that they tell you that you're Gatorade?
Yeah, so same issue. When you're sick, you are also getting rid of a lot of electrolytes through your waste in your body, so your urine and things like that. And if you're not eating foods, you're not getting those electrolytes back. So if you're eating food, there's no reason to drink Gatorade. But if you're so sick that you don't want anything, or you're throwing up, or you're having diarrhea, you're getting rid of all those sodium and potassium and salts through all of that grossness. And so you need to get some of that back into your body. But if you're eating, there's no reason to. Have you ever had Pedialyte?
Yeah.
So it's really gross. Do you know why it's so gross? Because the goal is to get the most electrolytes in you with the smallest volume, because little kids who are sick are really not going to want to drink a whole lot. And so that stuff is loaded up with salt, and having like juice that has a lot of salt in it is kind of gross tasting. So that's why that tastes gross. All right, so that's electrolytes. Yeah, so do not believe the marketing. Gatorade doesn't give you energy because of its electrolytes. It does give you energy, but that's just because it has a lot of sugar in it. So if you have like sugar-free Gatorade, it's not giving you energy. It's just replacing your electrolytes. It depends how they're advertising it. If they're advertising that it gives you energy, then yeah. But if they're advertising that it gives you energy because of sugar, that's true. I mean, all sugar is energy. So they could, Coke can advertise that they give you energy and you should drink it for sports, but it doesn't mean that it's accurate. Yeah. Okay. So we talked about making these solutions. We talked about electrolytes. Now let's look at how we actually measure how much how we talk about how much solute is in a solvent. Because you can imagine this becomes a problem. So far, when we talk about pure substances, measuring them is no big deal. If you have some solid salt and you need a certain number of moles of it or whatever for your reaction, you just do the calculation, you weigh it out in the balance, and that's how much you've got. Liquids, the same thing. We can also use volume for liquids. Gases, we talked about on Tuesday, are a little trickier because we have to use pressure, but still, you just directly measure how much you have. Solutions are different still, because the same solution, the same type of solution, could have different amounts. So let's say we dissolve 10 grams of sodium chloride in water versus dissolving 5 grams of sodium chloride in water versus dissolving 15 grams of sodium chloride in water. Those are all going to look the same. They're all going to just be clear-looking solutions. They're all going to have roughly the same mass by volume. Their density will change a little bit, but not a whole lot. And they'll all be sodium chloride solutions in water. But if we want a specific amount of that sodium chloride, we need to know how much is in the water. And the measurement that we use for that is called concentration. Concentration is always, there's a couple exceptions, but for our purposes, always a measure of how much solute is in a given amount of solution. So if you have 10 grams of a sodium chloride solution, or you have 10 milliliters of a sodium chloride solution, how much actual sodium chloride is in that? That's what we want to know, and that's what concentration tells us. What gets a little tricky about this is there's lots of different ways to describe that, to describe how much of one thing is in the other thing. And depending on the situation and what you're doing, one way of talking about that may be more helpful than another way. And so we're going to look at a few different measures of concentration and talk about what they're used for. This creates often a big mess, especially in something like medicine, because tradition plays a big role here. However something was measured for 200 years, they still use that way of measuring it, but that might be totally different from this other thing that looks the same. So if you ever notice, if you look at especially solutions, liquid solutions in medicine, things like fluid bags, liquid medications, they often have lots of different types of measurements, and that's not specifically to be annoying, but you do have to have, it's just because that's how it was, but you have to be able to then switch between these different types of measurements and understand that they're different, otherwise you could potentially hurt somebody by accident. So let's look at some different measures of concentration and then talk about how we can interconvert between them. The first ones we're going to look at are probably the easiest ones, and they're all percentages. So we're going to look at 3% based concentration measures. The first one is called percent by mass. And this just answers the question, what percent of the total is solute? And then the rest of the percent is solution, everything else. So in percent by mass, which is written percent m divided by m, percent m over m, you just make a simple percentage of the solute and the total solution. And since that's a percentage, we multiply by 100%. And we call that percent by mass, or mass percent. So in this way, you're just saying what percent of the total mass is solute. The units for mass aren't important, they just have to match because you want them to cancel out because percents don't have units. So if you want to use grams, it's grams of solute over grams of solution. You can do it with pounds, whatever. Kilograms, it doesn't matter. Okay. The trickiest part of percent by mass is remembering that the denominator, as is true in all these concentration measurements, is the total solution, not just the solvent. So the total solution in the denominator. So if you mixed, let's look at an example here. 5 grams of sodium chloride, or we'll say dissolved in. Five grams of sodium chloride dissolved in 100 grams of water is not a 5% solution because you need the total mass to divide by. So the way that you would solve that is you would say the percent by mass is 5 grams of solute divided by 105 grams of solution, the total mass of the whole solution. Try that. So 5 divided by 105 is 0.0476 or 4.76%. So there's nothing tricky about this. It's just a percentage, just like any other percentage. The fact that it's a solution doesn't change anything in the calculation. The next calculation is the exact same, but using volume instead of mass. And the way we denote that is V over V. So this is useful when you have two liquids that you're making a solution of. Rather than weighing them, you can measure them by volume, and that can be more helpful for whatever your application is. So everything is the same, but we substitute the word mass for solution or for volume. So we now have the volume of the solute divided by the total volume of the solution times 100%, and that's your percent by volume. So when you have a liquid that you're mixing with water, this is often the measurement that's used because it's easier to measure liquids by volume sometimes than by mass. So when you see things like alcoholic drinks are always reported in ABV, or alcohol by volume, which is a percent by volume. So that's the percent of the solute, in that case the ethanol, divided by the total volume of the solution, which is everything else. Volumes percent is often not equal to mass percent, because most compounds other than water have a density that is not 1. And so the volume that they take up is going to be a little bit different. Okay, so I think those make sense? Can you calculate percentages that way? All right, the last one is kind of the weird one. And it's called percent mass by volume, or percent M over V. So it's sort of a common, still a percentage, but the problem with the first two is, as we've said a couple times, it's easier and more convenient to measure solids by mass, and it's easier and more convenient to measure liquids by volume, especially when you have a solution. So what often happens is you want to make a solution by putting a solid solute in a liquid solvent like salt and water. But then you want to know how many grams of sodium chloride a particular amount of the solution has. And so you use mass by volume for that concentration so that you can measure your solution by volume, but it'll tell you how much mass you have. Percent mass by volume, because it kind of mixes units like this, requires specific units, and that is grams of solute per 100 milliliters of solution. And that's written as percent M divided by V. So it's grams per 100 milliliters. It just happens to come out as a percentage. When you do this calculation. So let's look at an example of this one. So we're going to calculate the mass by volume percent of 0.3 liters of a solution containing 15 grams glucose. Okay? So you can see how that's an easy way to make a solution. You measure out the 15 grams of glucose, and you just add water until the total solution volume is up to 0.3 liters. Now to do that, we can look back at our equation here and we can say, okay, percent M over V equals grams of solute, which in this case is glucose, divided by milliliters of solution. So we can plug those numbers in. The only change here is that our volume is given in liters, not milliliters. So we have to do that conversion. 0.3 liters is 300 milliliters. So we go 15 divided by 300, and we get 0.05, which is 5% glucose by volume. 5% mass by volume glucose. So it's calculated the exact same way as any of the other percents. Amount of solute divided by amount of solvent, and then turn it into a percent. That's always the same calculation for any of these three. The only difference is we have to make sure that the solute amount is in grams and the solvent amount is in milliliters for this to work properly. So let's highlight that, make sure you have grams and make sure you have milliliters, and then everything's good. Okay, so those are the three percentages. Think you can do that, maybe? We'll practice a little bit too. Well, let's throw our last concentration measure in here also. The fourth concentration measure we're going to look at is important when it's called molarity, and it's just written as a capital M. Usually sometimes kind of a fancy looking M, like a cursive sort of M. I think in the book it's just slightly italic. Molarity is a different type of concentration, just like moles is a different way of accounting for what you have. The other three were all about mass. We're all about grams, how much of something you have in mass. But sometimes you don't want to know the mass, you want to know the count. How many of these things do you have? That's why we use moles in the first place when we talked about chemical reactions. When you want to count things, you need moles. Same thing with solutions. If you want to count how many actual ions or molecules or whatever are in your solution, those last three measurements don't really help you much. But molarity does. Molarity is defined as moles of solute divided by liters of solution. So it's the same type of measurement, amount of solute divided by amount of solution. The pen's being weird today. Moles of solute divided by liters of solution. The difference with molarity is just in the unit. So now we're going to use moles instead of liters. Luckily, we spent time working on all of this so that you can easily convert between grams and moles of various compounds. So you can use those skills to calculate molarity. So let's try it. We're going to use the same numbers as before. So calculate the molarity when 15 grams of glucose is dissolved in 0.3 liters of solution. So this was a 5% mass by volume solution. Let's see what it is in molarity. All right, so to calculate the molarity, we need moles of solute divided by liters of solution. We have grams of solute and we have liters of solution. So far all we can do is put the 0.3 liters down there because we've got that. And we need to figure out how to get moles of glucose for the numerator. So to do that, we need to convert grams to moles. And to do that, we need to know the molar mass of glucose. So glucose, the formula of glucose is, we could look it up, it is H12O6. So you could add that all up, 6 carbons, 12 hydrogens, 6 oxygens. I will just tell you that the molar mass or the molecular weight of that is 180 grams per mole. So if you add up those 6 carbons, 12 hydrogens, and 6 oxygens, you get 180 grams per mole. So we can use that to convert from the grams that we're given to moles, just like we've been doing for a while. (15 grams C6H12O6), and we want to get rid of grams and instead have moles. So we use the molar mass to do that. The molar mass tells us there are 180 grams per each mole. So that means that 15 grams is 0.083 moles of glucose. So now we have our moles. We can divide moles by liters and get molarity. 0.083 moles per 0.3 liters. So our molarity is 0.083 divided by 0.3. Oops. 0.277 m. And the way we say that is molar. So it's not 0.277 moles. We didn't calculate moles. We took the moles, we figured out how much there was per a certain given amount of solution, and we now have a 0.277 molar glucose solution. That's how molarity works. Okay, here's one for you to try. Calculate the molarity and percent mass by volume when 2.33 grams of potassium chloride are dissolved in 250 milliliters of solution. So use the definitions that we just went through. You'll have to convert a few units and see if you can come up with the molarity and the percent mass by volume for this particular solution. Nope, it's now 250 milliliters of solution. So you have to figure out how to get that at the end.
What do you mean when it says like grams of solute over 100 milliliters of solution?
It's the way that we do the percentage, because grams per 100 grams would be like a percent, like per 100% always means per 100. So that's what the unit means. For actual calculation purposes, it's just grams divided by milliliters and then turned into a percent.
you divide the 250 by the 100?
Nope. Because the 250 is your milliliters. So that just becomes the denominator for that particular calculation. For molarity, you need to turn it into liters, right? Almost. So that's the correct calculation. We can return that.
Yeah, I did.
Oh, that is, yes,
Yeah.
yes, that's right. Yeah.
What was my bad?
Yep. Nope, you're right, you're right.
When you're finding molarity, can you go up each?
Yep.
So when you're finding molarity, are you always going to divide it by the molar mass? Just what they give you by the
If you're given grams.
Okay.
If you're given moles, you just use whatever they give you.
Right.
So you can get both those numbers, and then we'll go through the calculation together. Do you give this a try or still working on it? Anybody?
These are like chemical bottles, and it says like 0.03 m.
Yep. Telling you how much solute is in there. All right, let's give it a try. So let's do the mass by volume first because it's a little easier because we already have the units, grams and milliliters. Percent mass by volume is always going to be just the grams divided by the milliliters. Turned into a percentage. So 2.33 divided by 250 is 0.00932, which is 0.932%. And make sure when you report that you're always reporting it with the full units. So it's important that that percentage is M over V because as we've talked about, there are 3 different types of percentages that are all a little bit different in how they end up getting calculated.
So when I was doing it, I actually turned it into liters. That I had 9.2.
Right, so you're off by 10 that way.
So always don't turn it into liters.
With percent mass by volume, you leave it in milliliters in the denominator. Yep. So for the next one is when we do need to turn it into liters, which is molarity. So to get the molarity is going to be the moles of KCl, moles of solute, divided by the liters of solution. But we're given grams and milliliters. So in order to do this, we have to get a little more room here. We have to get that 2.33 grams of KCl into moles, and we have to get that 250 milliliters into liters. You can't calculate molarity until you've got moles and liters. So to do this, we do what we did before. We use the molar mass to calculate the moles of KCl. That's 2.33 grams. Convert from grams to moles. Molar mass of KCl is 39 plus 35.5, which is going to be what, 74.5? All right. Okay. So 74.5. .031 moles of KCl. 312, but I ran out of room. Okay, so now we've got our moles. And then on the denominator, we're going to have our solution in liters. It's 250 milliliters, which we convert to liters by dividing by 1,000. So 0.250 liters. So that makes our molarity 0.124. And so we would say we have a solution that is 0.124 molar KCl.
You wouldn't multiply it by.
Right, because this is not a percent. So you would not multiply it by 100. Molarity is not a percent, it's just the molarity. All right. So the reason that a couple reasons that this unit is so useful. One is when you're doing chemical reactions, you care more about moles than about grams because you need to match up the moles. So think about that experiment we did a couple weeks ago, the chemical reactions one, where you had to figure out the ratio of the chemical reactions. If we were using solid reactants, that would be a pain because you couldn't just measure out the same amount of each and then like figure it out. But we were using solutions that were both the same molarity. So that ensured that 1 drop of one and 1 drop of the other meant that the reactants were matched up exactly 1-to-1 in the equation. So using the molarity allows you to count individual atoms or individual moles of molecules by measuring out certain amounts of solution. This is also important in medicine because of something called osmotic pressure. All right. So we're going to do osmotic pressure. We're going to do a lab on osmotic pressure next week. But the basic idea is you know what? Let's not talk about this right now. Let's do it next week. I don't want to confuse you when we're still focusing on these calculations. Let's keep working on this stuff for today because we only have 25 minutes left. And we'll get into osmotic pressure next week. So I want to show you, or I want to give you 3 more definitions. Saturated unsaturated and supersaturated. Does anybody know what these mean with respect to solutions? Like, what's a saturated solution? How highly?
Very highly.
You could be more specific than that, actually. It's the most concentrated that is possible for a given solute. So a saturated solution is the highest possible concentration for a given solute. And we also should note that this is at a given temperature. Because solubility, the ability for something to dissolve in something else, changes with temperature. Different solutes are different. Salt, for instance, doesn't make much of a difference how hot or cold it is. Solubility doesn't change that much. But sugar, it changes a whole lot. If you've ever tried to dissolve sugar in like iced tea compared to hot tea or hot coffee, it's much harder to get it to dissolve in the cold solution than in the hot solution. And that's because its solubility changes with temperature, with heat. So an unsaturated solution is anything less than that. So there is you could still add more solute and get it to dissolve. To make a truly saturated solution, what you would do is have a whole bunch of excess solute, so much so that it actually just sits in the bottom undissolved. And that way, no matter what happens with evaporation or with other weird stuff, getting water from the air, whatever, it will always recorrect from the extra stuff on the bottom, and there will always be exactly as much in the solution as can fit. And an unsaturated solution would always have nothing remaining, no solid solute remaining on the bottom of the container. Supersaturated solution is a little bit weird. Has anybody ever heard of that before? You know what that means? Yeah.
It's like oversaturated, so some of the solids like not.
Yeah, what happens is, so saturated is the highest concentration for a given temperature. If you raise the temperature, you can actually get more to dissolve because higher temperatures make more dissolve. But if you raise the temperature and then you really carefully and slowly cool it back down to the lower temperature, you can actually trap the extra solute still in solution. So you can have a solution that has too much solute for what it should really take at a lower temperature. And what happens then is any, what we call a nucleation site, any little like inconsistency in the container or a little bump, or if you put like a string in it or something, it'll automatically start to precipitate, and all that extra will start coming out in solution and precipitating. Yes?
So is it like viscous? Like
That, not quite, because in that case you've got so much sugar that there's actually more sugar than water. So you're making, but you can make a supersaturated solution with sugar. And what ends up happening is as you cool it, the sugar crystallizes out. So that's how you make like rock candy, if you've ever seen that, the candy that sort of grows in crystals on the stick. That's because it's supersaturated, so it has this ability to come out. It's not as important of a definition as the other two. It's just kind of an unusual situation, but it is important to know what saturated versus unsaturated solutions are and what they look like. All right. Let's look at how to get the amounts that you need from the concentrations that you're given. Oops. Lost my spot again. Sorry. Okay. So we calculated the molarity, but what happens when we want to know something like, let's say we actually have a real example here. We've got an equation. So if you add acid HCl to sodium carbonate, you'll produce carbon dioxide gas, water, liquid water, and sodium chloride, aqueous sodium chloride. This equation is not balanced. I think I just need a 2 here and then, no, and then here. And then it works. Yeah. Okay. So let's say we figured this all out and we've got, we figured out our mole ratio and we figured out in this equation that we need, oops, that's not how you spell we need 6.25 moles of HCl to react with the sodium carbonate that we have. So I didn't get that from the equation or anything, just a made up number. That's how much we figured out. We used mole ratios. We figured out we need 6.25 moles of this to react. How much of each solution would we need? So here are your solutions. Our first solution is a 3 molar solution. And our second one is a 9 molar solution. So 2 different concentrations of hydrochloric acid. A 3 molar solution of hydrochloric acid and a 9 molar solution of hydrochloric acid. We need 6.25 moles. So how do we figure that out? Well, the key to this is remembering the definition of molarity. Here, I'm going to move this so we have a little more room. So if you have a 3.0 molar solution of HCl, if we remember our definition of molarity, that means that there are 3.0 moles of HCl per every 1 liter of solution. All right, that's what molarity means. That's the definition. So we can actually use that like a conversion factor, just like all the other conversion type problems we've done, to convert from moles to liters. So we can say, all right, we want 6.25 moles of HCl. In order to get that much HCl, we have to go from moles of HCl to liters, because that's how we're actually going to measure it out, liters of solution. And the molarity tells us that that's 3 moles per liter. Okay, so 6.25 divided by 3, 2.08. So in order to supply those 6.25 moles, we would need 2.08 liters of solution. And let's think about that logically and see if it actually makes sense. Our 3 molar solution tells us that there are 3 moles in every liter. We want a little more than 6 moles, so it means we need a little more than 2 liters if there's 3 moles per each liter. Does that make sense? All right, try the next one then. What if you had a 9 molar solution? How much of that solution would you need? All right, what do you think? Got it? What'd you come up with?
0.6.
Sounds about right. So let's think about it first, about what kind of number we should get before we mess with the calculation, because that's always a good way to check if you did it right. If we again need 6.25 moles, and we have 9 molar solution, does that mean we're probably going to need more or less than a liter? Less, because it's 9 moles per liter. We need 6-ish moles, so we need a little bit less than 9. So we expect our number to be less than 1 because we need less than 1 liter. All right, so let's do that same calculation. This time we've got 9 moles of HCl per liter of solution. So we'll need less than a liter. We'll need 0.694 liters of solution, or 694 milliliters this time. All right, see how that works? Okay. You want to try one more, or are you good? How many people say one more? Couple. All right, let's do one more. Why not? All right, this one's from the book. So this one we're going to look at one opposite way of solving this. And if we don't finish going through it today, we can. But how much silver nitrate in grams to prepare 1 liter of a 0.3 molar solution? How much silver nitrate in grams is needed to prepare 1 liter of a 0.3 molar solution? Now, this isn't exactly the same as the other ones, but if you think about the definition of molarity, put in your equation there, put in what you know, what you don't know, and then see if you can figure out the unknowns.
It's just molarity problem.
Mm-hmm. But you're not calculating the molarity or the volume needed. You're calculating how much mass is needed to prepare. All right, we've only got a couple minutes left, so let me show you how this works. So once again, you want to start with that definition of molarity. You're told the concentration, 0.3 molar, and that tells you that there are 0.3 moles of silver nitrate in every liter of solution. That's what the molarity tells you. All right, since we're just being asked to prepare 1 liter of the solution, all we need to know is how many grams are in 0.3 moles of silver nitrate. That's a simple enough conversion. We can use the molar mass just as we've done a bunch of times before. So 0.3 moles of silver nitrate and we're going to go from moles of silver nitrate to grams of silver nitrate. So we need to come up with a molar mass for silver nitrate. Did anybody get that calculated?
170.
170?
Yeah.
Okay. I don't know. I'll take your word for it. Is that anybody else do it? Does that sound right? Okay. So 0.3 times 170 is 51 grams of silver nitrate. So you would need 51 grams of silver nitrate. You just dissolve that until the solution, the total solution volume is 1 liter. And then you're good. You've got a 0.3 molar solution. That's how that works. All right. Quiz Tuesday will be on all the stuff from this week. So the gases, behaviors of gases, and the different relationships, like what happens when you change volume or pressure or temperature. And then the stuff from today on solution concentration as well.
Do you ever upload a place to put the concept lab?
Yes, there's a spot for dropping the fifth lab. If you still need a little time to work on that, that's fine. You don't have to put it in right away.
Yeah.